A spacecraft can sail to the stars without a single drop of fuel. This is the breathtaking potential of light sail technology, a concept championed by the visionary Carl Sagan. By the end of this journey, you will understand the complete blueprint for building humanity's first interstellar ships. We will uncover the physics that allows light to push a vessel and confront the immense challenge of constructing a sail thinner than a soap bubble. How close are we to turning this cosmic dream into a working machine? That faint warmth you feel on your skin from sunlight is actually a physical push. Each particle of light, a photon, carries a tiny amount of momentum, and when it bounces off a surface, it gives that surface a minuscule kick. To propel a spacecraft, we need to amplify this effect from a gentle nudge into a powerful, continuous thrust. The physics hinges on a beautiful equation, P equals E divided by C. This means the momentum, P, a photon delivers is equal to its energy, E, divided by the speed of light, C. Since the speed of light is such an enormous number, the push from a single photon is almost laughably small. But when you have a powerful, focused laser firing countless trillions of photons every second at a vast, mirror-like sail, those tiny pushes add up to a substantial force. This is the principle of radiation pressure, and here is the brilliant part. If the sail is a perfect reflector, the physics gets even better. When a photon bounces off the sail, it not only gives its momentum to the sail on the way in, but it also gives an equal amount of momentum on the way out as it recoils. This double push means a perfectly reflective sail can, in theory, be twice as efficient as one that simply absorbs the light. This is not just a classroom thought experiment. Initiatives like Breakthrough Starshot are pouring serious research and investment into turning this concept into a working machine. Their vision involves a ground-based laser array, a kilometer-wide, focusing its immense power on a lightsail only a few meters across. The key advantage is revolutionary. The spacecraft carries zero fuel. All the propulsive energy comes from the external laser, meaning the craft can be incredibly lightweight, allowing it to achieve speeds previously only dreamed of, a significant fraction of light speed. But this incredible potential rests on solving one of the most difficult engineering puzzles ever conceived, building that sail. To catch this laser beam effectively, the sail must be enormous, perhaps kilometers across, yet it must also be almost unimaginably thin and light, a challenge that pushes the very limits of modern material science. Building a structure the size of a city block from a material thinner than a soap bubble is the monumental challenge facing light sail engineers. This is not about traditional spacecraft metals, which would be far too heavy. The ideal sail demands a trifecta of nearly impossible properties. It must be almost perfectly reflective to maximize the push from the laser. It must be incredibly lightweight, with a target mass of less than 1 gram per square meter, a density so low it is difficult to even conceptualize. And it must possess tremendous tensile strength to survive the sudden, brutal acceleration and the unforgiving environment of deep space, all while being pelted by microscopic dust grains traveling at relativistic speeds. To meet these demands, scientists are turning to materials engineered at the atomic level. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, offers phenomenal strength and stunning lightness. Synthetic diamond nanofilms, created layer by layer, promise exceptional durability and high reflectivity. Then there are the metamaterials, substances whose structure is artificially designed to manipulate light in ways nature cannot, potentially creating the ultimate mirror for our laser beam. The entire design is a constant battle between two numbers, areal density and tensile strength. The sail must be as light as possible to accelerate quickly, yet strong enough not to tear itself apart under the force of a gigawatt laser. One of the most pressing vulnerabilities is micrometeoroid damage. A single impact from a speck of dust, smaller than a grain of sand, could rip a fatal gash in the sail. This has spurred research into self-healing materials, smart composites embedded with microcapsules of reactive chemicals that could automatically seal a puncture, much like how a scab forms on a wound. But creating a few square centimeters of this advanced film in a lab is one thing. How do we manufacture a perfect kilometer-wide sheet of it in space? The answer may lie in revolutionary new processes, perhaps involving swarms of robotic assemblers or novel spin casting techniques that can construct the sail directly in the vacuum of space, avoiding the impossible task of folding and deploying it from a tiny rocket. Even the most complex solar arrays ever unfurled in orbit would be simple origami compared to the challenge of a light sail. Packing a structure the size of a city into a spacecraft no larger than a shoebox requires a deployment sequence of almost impossible precision. One leading concept relies on spin deployment, where the entire package is set rotating. Centrifugal force gradually pulls the tightly folded sail material outward, like a dancer's skirt flaring in a spin. This elegant motion must be perfectly controlled, however, as a single snag could send the gossamer thin film into a catastrophic tumble, twisting and tearing itself into useless ribbons. Inflatable booms offer another path, where rigidizable tubes unfold to create a supporting skeleton for the sail. Yet these, too, carry the ever-present risk of a malfunction, a single stuck valve dooming the entire mission. The real-world experience from missions like NASA's Near-Earth Asteroid Scout provides a sobering glimpse into these hurdles, where engineers grapple with the unpredictable dynamics of controlling a structure so large and so flexible that it behaves more like a phantom in the solar wind than a solid spacecraft. To tame this ethereal giant, we must look beyond rigid mechanics. The sail itself may need to be intelligent, woven with a network of sensors and actuators. Imagine smart materials that can change their shape autonomously, correcting for a developing wrinkle or steering the craft by subtly altering the sail's curvature, using the pressure of sunlight itself as a rudder. Successfully unfurling this vast silver sea is a triumph in itself, but it is only the prelude. The true test comes when the most powerful laser ever built switches on, and this delicate creation must hold its form under a force unlike anything nature has ever produced. The power of that laser beam would be unlike anything ever created by humanity. To push a sail to the stars, we need a light source of almost unimaginable intensity, a ground-based array spanning kilometers, firing a coherent beam of focused energy. This is the cosmic catapult, a phased array laser system with a power output measured in hundreds of gigawatts. For a moment, that single beam would consume more electricity than an entire nation, all focused onto a sail the size of a small town, but thinner than a single human hair. The physics of this interaction is a race against vaporization. Even a near-perfect reflector will absorb a tiny fraction of that immense energy, and that tiny fraction is enough to heat the sail to thousands of degrees in an instant. The sail must not only reflect light with phenomenal precision, but it must also radiate that absorbed heat away with incredible efficiency, or it will simply turn into a brief, brilliant cloud of plasma. And then there is the problem of the atmosphere. Our air is a turbulent, shimmering lens that would scatter and distort the most powerful laser beam, blurring its focus across millions of kilometers and rendering it useless. This fundamental limitation suggests the laser array itself may need to be built in the vacuum of space, or perhaps on the high, dry plateaus of Earth, where the atmosphere is at its calmest. Guiding this beam presents another monumental challenge. As the sail accelerates, it moves farther away at an ever-increasing rate. The laser must not only hit a target smaller than a pixel from light years away, but it must also lead that target, aiming not at where the sail is, but at where it will be when the light arrives. This requires a level of predictive precision that pushes the boundaries of our understanding of orbital mechanics and control systems. The entire acceleration phase is a breathtakingly short, violent event, a minute-long burst of power that must be flawlessly executed to fling a tiny craft toward the stars. But reaching another star is only half the mission. Once this tiny vessel is on its way, traveling at a fifth the speed of light, how do we guide it to its target, and how on earth do we ever hear from it again? Guiding this vessel is like trying to steer a single snowflake through a hurricane from thousands of kilometers away while it travels faster than any bullet. The navigation problem for a light sail probe is one of immense scale and subtle control. During its brief, furious acceleration phase, the craft must hold a perfect posture in the laser beam, a feat akin to balancing a coin on its edge in a gale force wind. The slightest tilt could send it veering catastrophically off course. One elegant solution lies in the sail's own design. By selectively darkening or lightening small segments of the sail, the craft can create differences in reflectivity. A darker patch absorbs more light and gets more push, while a brighter patch reflects more, generating a tiny torque that can be used to rotate the entire vehicle. It is steering by shading, a beautiful dance of light and shadow performed at relativistic speeds. Once the laser falls silent and the craft enters the long coast between stars, the challenge shifts from steering to knowing where to steer. Traditional star trackers and gyroscopes, the trusted navigational tools for satellites, begin to fail at such extreme velocities. The universe itself starts to look different. The phenomenon of stellar aberration causes the positions of stars to shift dramatically, bunching up ahead and spreading out behind, as if the probe is sailing through a tunnel of light. An onboard artificial intelligence would be essential, not just for processing this distorted star field, but for making autonomous decisions. A course correction command from Earth would take years to arrive, and by the time it did, the probe would be long gone. The machine must become its own captain, capable of recognizing its target system and making any final trajectory adjustments entirely on its own. This autonomous intelligence must then perform its ultimate task, to observe a new world and phone home across the void. The distances involved are so vast that a simple radio signal, carrying the precious data of a new planetary system, would be incredibly faint by the time it reached Earth. We would need an incredibly sensitive network of radio dishes spread across the solar system, listening for that one tiny whisper lost in the cosmic noise. The entire endeavor hinges on a fragile chain of technologies, each one pushing the boundaries of the possible, from a sail thinner than a soap bubble to an AI navigating by a distorted sky. And if we can solve the puzzle of getting it there and hearing its message, we then face the final, profound design challenge, crafting the tiny eyes and ears that will actually see another Earth for the first time. That faint whisper of data is the entire purpose of the mission, a single laser beam carrying the first close-up images of another world, sent from a transmitter smaller than a coffee cup across trillions of kilometers of empty space. The communication challenge is perhaps the most daunting of all, a problem of scale that defies everyday intuition. The power required for a radio signal to be detectable over such a distance is immense, far beyond what the tiny probe's power source could ever provide. The solution is to trade raw power for incredible focus. Instead of a radio broadcast spreading out in all directions like a fading light bulb, the probe would use a laser, a needle-thin beam of light aimed precisely at our solar system. This laser communicator, likely powered by a tiny nuclear battery, might only output about 1 watt of power, roughly the same as a small Christmas tree bulb. But because that energy is concentrated into such a narrow beam, it does not dissipate as quickly across the void. Even with this brilliant focus, the signal that finally reaches Earth after its years-long journey would be astonishingly weak, a phantom signal containing just a few precious bits of information every second. Catching this interstellar murmur requires a listening ear of matching grand scale. We would need a network of radio telescopes spread across the globe, or perhaps in space, working in concert to form a virtual dish kilometers wide. Projects like the Square Kilometer Array are precursors to this very technology, designed to listen to the faintest whispers of the cosmos. The entire communication system is a delicate balance of 3 factors: the transmitter's power, the size of the receiving antenna, and the painstakingly slow data rate. To send a single high-resolution image might take weeks of continuous transmission, each bit of data a hard-won prize. One ingenious proposal is to turn the light sail itself into a giant antenna. After its arrival, the delicate sail could be reconfigured, its vast surface area used to focus the outgoing laser beam with even greater precision, boosting the effective signal strength without needing more power. This elegant repurposing turns the probe's greatest vulnerability into its most powerful asset. Every aspect of this communication chain pushes against the limits of physics, from creating a stable laser pointer that can hold its aim on Earth from light years away, to building a receiver sensitive enough to distinguish its signal from the background radio noise of the entire universe. Every byte of data it sends, from atmospheric spectra to surface maps, will have been gathered by a suite of instruments so miniaturized they would fit in the palm of your hand. What kind of eyes and ears do we give this tiny ambassador to see a new world for us? Every instrument on this interstellar probe must be smaller than a postage stamp and lighter than a raindrop. This is the ultimate challenge in scientific miniaturization, packing the capabilities of an entire research laboratory into a package weighing just a few grams. The goal is to maximize the scientific return from our first fleeting encounter with another solar system, a fly-by lasting mere hours at a significant fraction of light speed. So what essential tools do we send? A high-resolution camera is paramount, its tiny sensor designed to capture the first detailed images of an exoplanet's surface, transforming a distant dot of light into a world with continents and oceans. Alongside it, a microscopic spectrometer would break down the light from that planet's atmosphere, searching for the chemical fingerprints of water vapor, methane, and oxygen, potential signs of a living world. A miniature magnetometer, no larger than a speck of dust, could extend its senses to map the alien star's magnetic field, while a dust analyzer would sample the interstellar medium itself, tasting the raw material between the stars. The technology to build these devices is already emerging from labs specializing in micro-electromechanical systems, or MEMS. Engineers are creating cameras where the entire optical assembly is etched onto a single silicon chip, and sensors so small they are practically invisible. Powering this entire suite of instruments presents another profound constraint. There is no room for solar panels, and the journey will last for decades. The only viable solution is a tiny radioactive power source, a nuclear battery that generates a trickle of electricity from the steady decay of a small pellet of plutonium or a similar isotope. This power source must be rugged, reliable, and safe, capable of operating in the deep cold of interstellar space for generations. Every component, from the camera lens to the computer processor, must be hardened against the relentless bombardment of cosmic radiation, subatomic particles that can scramble electronics and degrade materials over time. The entire spacecraft is a testament to fragility and resilience, a collection of microscopic wonders embarking on a macroscopic journey. Its successful arrival at another star represents a triumph of human ingenuity, but it also forces us to confront a deeper, more philosophical question about the nature of such a one-way mission and the legacy it leaves behind among the stars. A tiny craft on an interstellar voyage faces a silent, invisible gauntlet for decades. The space between stars is not a perfect vacuum. It is a diffuse sea of high-energy atomic particles and microscopic dust grains, each one a potential mission-ending hazard at these incredible speeds. The primary threat comes from galactic cosmic rays, atomic nuclei accelerated to nearly the speed of light by distant supernova and black holes. These particles are so energetic they can punch straight through solid materials, disrupting and permanently damaging delicate computer chips. Without protection, the probe's brain could be scrambled long before it reaches its destination. Engineers counter this with a combination of strategies, starting with radiation-hardened electronics, circuits specifically designed to resist this kind of subatomic bombardment. The physical shielding itself cannot be thick or heavy, so scientists are investigating innovative materials like hydrogen-rich polymers. Hydrogen atoms are so small they are excellent at scattering incoming radiation, acting like a subtle but effective bumper in the cosmic pool hall. Then there is the threat of impact. A dust grain no larger than a single bacterium, when striking a vessel moving at a fifth the speed of light, would release energy comparable to a small nuclear bomb. A direct hit would instantly vaporize the entire probe. The only defense is to make the craft as small a target as possible, often conceptualized as a spherical or needle-like shape to present a minimal cross-section. Some designs even propose a distributed architecture where the critical components are separated across a small cloud of interconnected modules, so a single impact only disables a non-essential part. Research into self-healing materials extends to the electronics as well, with circuits that can reroute signals automatically around a damaged section, much like a stream finding a new path around a fallen log. This is not about building an armored tank, but about creating a resilient and redundant system that can absorb a certain amount of punishment and keep functioning. Surviving the journey, however, is only possible if the initial aim is true. The precision required for this interstellar shot is almost beyond comprehension. A launch timing error of just 1 second could mean missing the target star by millions of kilometers. The trajectory must account for the gravitational pull of every planet in our own solar system, the pressure from the solar wind, and even the subtle push of the light from the target star itself. It is a calculation of phenomenal complexity, a billiard shot across light years where the cue ball is a laser beam and the target is a moving dot in an ocean of other dots. The trajectory to Alpha Centauri is a 4-light-year shot where the target is not a stationary bullseye, but a star moving at over 60,000 kilometers per hour through the galaxy. This proper motion means you cannot aim at where the star is now. You must aim at where it will be in 20 or 30 years when your tiny probe finally arrives. The calculation is a breathtaking synthesis of orbital mechanics and predictive astronomy, requiring a launch window so precise it might only recur every few years. Even the initial boost from the laser is not a simple shove. As the sail accelerates away from Earth, the gravitational pull of the Sun and the planets will subtly bend its path, a factor that must be precisely calculated and integrated into the launch vector. An error in the initial angle of just a few thousandths of a degree would, over such a vast distance, cause the probe to miss its target star by a distance greater than that between the Earth and the Sun. To refine this celestial billiard shot, mission planners might even incorporate a gravity assist, using a close flyby of Jupiter to slingshot the craft, gaining an extra kick of velocity for free before the main laser even fires. This maneuver adds another layer of complexity, demanding perfect timing between the planetary alignment and the laser firing sequence. The astrophysics involved is a dance of immense forces and minuscule adjustments, where the most powerful laser ever built must be aimed with the delicacy of a watchmaker. But achieving this perfect shot carries a price tag to match its ambition. The development and construction of the ground-based laser array alone could cost hundreds of billions of dollars, a figure that rivals the gross domestic product of entire nations. This single system, a kilometer-wide phalanx of lasers and optics, would represent one of the most expensive and complex engineering projects in human history. And the laser is just one component. The cost encompasses the research into the sail materials, the development of the miniature probes, the global network of communication dishes, and the decades of operational support. Funding such an endeavor would likely require an unprecedented international consortium, a sustained global investment in a mission whose scientific return would not be realized for a generation. This forces a profound question about our priorities as a species. Are we willing to collectively invest in a project that offers no immediate reward, whose ultimate success will be witnessed not by its architects but by their children? The economic challenge becomes not just a matter of accounting, but a test of our long-term vision. The financial scale of an interstellar light sail mission is almost beyond earthly comparison. Think of the combined annual budgets of every major space agency on the planet, sustained not for a year but for decades. This monumental investment would be directed toward three colossal pillars of development. First is the research and development for the laser array itself, a kilometer-wide phalanx of amplifiers and optics requiring breakthroughs in power generation and thermal management. Second is the creation of the sail material, a manufacturing challenge that demands entirely new, atomically precise industries. Third is the global infrastructure, including the network of communication dishes needed to hear the probe's faint whisper from the stars. The total cost could easily reach hundreds of billions of dollars, a figure that forces us to rethink how humanity funds its most ambitious dreams. One compelling model is an international consortium, akin to the International Space Station but on a far grander scale, where nations pool resources and share in the scientific bounty. Public-private partnerships like the breakthrough initiatives funded by philanthropic visionaries offer another path, leveraging private capital to accelerate high-risk research. There is also a powerful economic argument to be made beyond mere discovery. The technological spin-offs from such a project would be profound. The quest for a perfectly reflective sail could lead to new types of optical coatings that make solar power far more efficient. The advanced lasers could revolutionize medical imaging and data transmission. The miniature sensors developed for the probe could lead to new generations of medical diagnostics and environmental monitors. These secondary benefits could ripple through our global economy, creating new industries and capabilities that repay the initial investment many times over. Historically, such grand endeavors are not without precedent. The Apollo program at its peak consumed nearly 4.5% of the United States federal budget. Adjusted for today's economy, that represents a commitment of hundreds of billions of dollars, all directed toward a goal that captured humanity's collective spirit. A light sail mission represents a similar leap, not just for a single nation but for our entire species. Yet securing the funding is only one part of the earthly challenge. Once the resources are assembled, We must then navigate a complex web of international law and policy that was never designed for ships that sail between the stars. A laser capable of propelling a starship is, by its very nature, a device of immense and ambiguous power. Its beam, visible across the solar system, would inevitably be scrutinized through the dual lenses of scientific wonder and geopolitical caution. The foundational document governing all such activities is the Outer Space Treaty of 1967, which firmly states that the exploration and use of space shall be carried out for the benefit of all countries and shall be free of weapons of mass destruction. While a propulsion laser is not a weapon by design, its potential for dual use cannot be ignored. A beam that can push a sail could, in theory, be redirected, its power used to disable other satellites or even influence objects on Earth. This creates a pressing need for new international agreements, specifically governing the operation of such high-power systems. These treaties would need to establish transparent protocols for when and where the laser is fired, ensuring its aim is always toward the stars and never perceived as a threat. The legal challenges extend far beyond the launch. Securing a dedicated and protected band of the radio spectrum for the mission's interstellar communications is another critical diplomatic hurdle. This signal will be incredibly faint, and any interference from future satellites or terrestrial networks could drown out the precious data from our distant probe. Nations would need to collectively agree to preserve this quiet channel in the cosmic airwaves for decades, a testament to long-term international cooperation. Furthermore, the principle of planetary protection becomes paramount. What if the probe, by some remote chance, were to impact a world with a potential biosphere? Strict protocols developed through bodies like the United Nations Committee on the Peaceful Uses of Outer Space would be essential to sterilize the spacecraft, minimizing any risk of forward contamination. This ensures that our first mission to another star is one of pure discovery, not an accidental invasion. The legal framework for this journey is not a secondary concern. It is the bedrock upon which the entire mission must be built, transforming it from a national project into a shared human endeavor. With these profound earthly questions addressed, we can finally lift our gaze to the sky and ask, where should this tiny ship sail? Our first destination among the stars is not a single choice, but a family of three. The Alpha Centauri system, our closest interstellar neighbor, presents a cosmic crossroads for explorers. Within this triple star system, we find two compelling yet very different paths. The first leads to Proxima Centauri, a small, faint red dwarf star just over 4 light-years away. Its immense appeal lies in Proxima Centauri b, a confirmed, rocky world orbiting within the star's habitable zone, that temperate region where liquid water could theoretically exist on the surface. A flyby of this world offers the tantalizing possibility of glimpsing a potentially habitable planet, of analyzing its atmosphere for the biosignatures of life. However, a red dwarf's habitable zone is a turbulent place, subject to intense stellar flares that could strip away any atmosphere, making the scientific payoff a high-stakes gamble. The alternative path points toward the system's twin suns, Alpha Centauri A and B. These are stable, sun-like stars, offering a more familiar environment to study. Centauri A is slightly larger and brighter than our own sun, while Centauri B is slightly smaller and cooler. A mission here would focus on understanding solar systems like our own, searching for undiscovered planets, and mapping the complex gravitational dance of a binary pair. Yet this dynamic duo creates its own challenges, as their orbital dance could disrupt the formation of planets or make stable orbits rare. The travel times between these options add another layer of strategy. Proxima Centauri is the closest target, but a flyby of the binary stars might require a more complex, longer trajectory. The data shaping this critical decision flows from observatories like the James Webb Space Telescope, which is already analyzing the light from these systems, searching for the chemical fingerprints of atmospheres around these distant worlds. This wealth of information means the scientific payload on our probe must be tailored to its target. A camera optimized for a dim red dwarf's world would be different from one studying a bright, sun-like star. But choosing one target feels like an impossible limitation. What if, instead of a single emissary, we could send a fleet, a swarm of tiny probes, each perhaps specialized for a different type of measurement, could be launched together? One could target Proxima b, while others veer off to study the twin suns, providing a multidimensional first look at an entire stellar neighborhood. This vision of a coordinated fleet transforms the mission from a daring snapshot into a comprehensive survey, ensuring that our first journey to the stars leaves no cosmic stone unturned. A single point of light sailing into the void carries all our hopes on one fragile package, but a flock of probes transforms that gamble into a calculated survey. The logic of a swarm is the logic of nature itself, the same reason 1,000 seeds are scattered to the wind to ensure that just a few take root. By launching not one, but thousands of these tiny nanoprobes, we build in a powerful redundancy. If one craft is lost to a dust grain or a system failure, a dozen others remain to complete the mission. This approach fundamentally changes the science we can conduct. Imagine two probes arriving at a distant planet minutes apart, their slightly different viewpoints allowing for stereoscopic imaging that reveals the true depth of canyons and the height of mountains in 3 dimensions. Or picture a cloud of 100 probes flying in formation through a star's magnetic field, their combined readings creating a dynamic, high-resolution map of forces invisible to a single observer. A swarm offers the ultimate flexibility, capable of splitting its forces to investigate multiple targets simultaneously. One group could veer toward the potentially habitable world of Proxima Centauri b, while another charts the turbulent space around the binary stars Alpha Centauri A and B, gathering a complete portrait of an entire solar system in one historic flyby. This is the vision behind initiatives like Breakthrough Starshot, which conceptualizes a launch of thousands of starships, each one a fully functional spacecraft on a credit card-sized wafer. The manufacturing challenge, however, shifts from crafting a single masterpiece to achieving perfect, cost-effective replication on an industrial scale. We would need to produce these probes not like bespoke watches, but more like microscopic computer chips, using advanced lithography and etching techniques to print entire fleets from silicon wafers. The launch and acceleration phase becomes a breathtakingly complex ballet. A single, powerful laser beam must push this entire cloud of sails without them colliding or casting shadows on one another. Each sail must maintain a precise, preordained position within the beam, a feat requiring tiny, onboard thrusters or sophisticated light manipulating surfaces to make minute corrections. The coordination is managed by a central computer system that treats the entire swarm as a single, distributed entity, ensuring they spread out into a safe formation as they accelerate toward the stars. Once on their way, this fleet becomes an autonomous, distributed intelligence. The sheer volume of data they will collectively generate presents its own monumental puzzle. How do we decide which probes send their information first, and what happens when their tiny transmitters all try to call home at once across the light years? That tiny chip of a brain faces an impossible task, making sense of an alien world in the few hours of a high-speed flyby with no one to ask for help. This is the challenge of onboard artificial intelligence, a system that must be both a brilliant scientist and a frugal accountant, all while running on less power than a night light. The core of the problem is time and distance. A command from Earth traveling at the speed of light would take over 4 years to reach Alpha Centauri. By the time it arrived, the probe would be far past its target. The AI must therefore be completely autonomous, capable of reacting to unexpected discoveries in real time. Imagine it flies past Proxima Centauri b and detects a sudden, unexplained spike of methane in the atmosphere, a potential signature of biological activity. A simple probe would just record the data. An intelligent explorer would recognize the anomaly's significance, immediately reprioritize its entire observation schedule, and dedicate its most sensitive instruments to investigate that specific chemical signal before the opportunity is lost forever. This requires a form of machine intelligence that goes beyond pre-programmed responses. Computer scientists are developing specialized processors for this very purpose, known as neuromorphic chips. Unlike traditional computers that process instructions in a linear sequence, these chips are designed to mimic the parallel, interconnected structure of a biological brain. This architecture is incredibly efficient, allowing them to perform complex pattern recognition like identifying a promising coastline or a strange atmospheric reading, while consuming a tiny fraction of the energy of a conventional computer. It is the difference between a pocket calculator and a human researcher, both in capability and in intuitive understanding. This AI's most critical job is data triage. The probe's instruments will gather far more raw information than its weak transmitter could ever send home. The system must therefore decide what is truly precious. A photograph of a featureless gas giant might be compressed heavily or even discarded, while a single, clear image of a cratered, Earth-like world would be tagged as top priority for transmission. This is not just data management, it is an act of scientific judgment performed by a machine light years from home. The development of this autonomous decision-making is what transforms a simple camera on a chip into an intelligent explorer, capable of choosing which pieces of a new solar system are most important for humanity to see. And after it makes those choices, the long, silent wait for its message begins, a test of patience spanning decades that challenges our very perception of a human lifetime. The scientist who designs this mission will likely never see its final results. This is the profound truth of interstellar exploration, a project that unfolds on a timeline spanning generations. Unlike any other scientific endeavor, its success depends not just on the engineers who build it, but on the children of those engineers and their children after them, who will be the ones to finally receive the signal from the stars. This introduces a unique sociological challenge, one of generational patience and institutional endurance. How do we manage a project whose active phase outlasts the careers of everyone who started it? The answer lies in creating a living legacy, a mission culture that is carefully passed down like a precious heirloom. Project management must shift from short-term milestones to the stewardship of knowledge, ensuring that the reason for a specific software command or a particular material choice is not lost to time. Modern digital archives, constantly updated and migrated to new formats, become the mission's long-term memory, preserving the collective intelligence for the future teams who will take the helm. Funding and political support must be insulated from the short-term cycles of election years and economic fluctuations, perhaps through an international trust designed to operate for a century or more. Public outreach and education are the bedrock of this longevity. The mission must capture the imagination of each new generation, inspiring young students who will one day become the engineers listening for the probe's whisper. We have historical precedents for such patience. The great cathedrals of Europe often took centuries to complete, with each generation of builders adding their stones to a foundation laid by their great-grandparents. all working toward a vision they themselves would never see finished. This interstellar mission is our modern cathedral, a testament to a belief in the future. It forces us to confront the legacy we wish to leave, not in stone, but in data and discovery for our descendants. And as we plan this legacy, we must also carefully consider the implications of sending our technology into a completely new stellar environment, ensuring our first step into the cosmos is taken with wisdom and foresight. A pristine alien ocean should not taste the chemistry of Earth. This is the core ethical principle behind planetary protection, a set of guidelines ensuring our exploration does not become contamination. For an interstellar probe, the risk is not conquest but a microscopic accident. Even after a decades-long journey through the harsh radiation of interstellar space, it is possible that a few tenacious Earth microbes, sheltered within the probe's electronics, could survive. If that probe were to crash into a world with a fragile, nascent biosphere, those terrestrial hitchhikers could, in theory, take root, forever muddying our ability to determine if any life we find is truly alien or just a trace of our own. To prevent this, the probe must be assembled in the cleanest rooms ever conceived, environments far more sterile than an operating theater. Every component would undergo a brutal decontamination process, perhaps bathed in intense radiation or heated in specialized ovens to temperatures that would incinerate any biological material. The mission trajectory itself becomes a moral choice. Planners would intentionally design the flyby to avoid any direct path that could lead to an impact with a potentially habitable world like Proxima Centauri b. The probe would sail past, a distant observer that never touches the new world it studies. This framework of responsibility is guided by international bodies like the Committee on Space Research, or COSPAR, which is already working to extend its planetary protection protocols beyond our solar system. This ethical foresight transforms the mission from a mere technical achievement into a promise, a commitment that our first step into the cosmic ocean will be taken with clean hands. With this promise in place, we can begin to dream bigger, to envision what a second-generation mission might look like once the first tiny sails have proven the way. That first successful mission is not an ending, but the initial tie for a cosmic railroad. Just as the first transcontinental railway began with a single track and eventually connected a continent, the first light sail probe could establish the foundation for a permanent interstellar highway. The initial laser array, built at immense cost, would become the first node in a solar system-wide propulsion network. Future installations could be constructed on the airless surface of the Moon, or built as massive, free-floating structures in the stable gravitational points between worlds. These stations would not be single-use monuments. They would be ports regularly launching swarms of specialized probes to a growing list of target stars. Each mission would build upon the knowledge of the last, creating a continuous stream of discovery flowing back toward Earth. The probes themselves would evolve, growing more sophisticated with each generation, carrying more advanced sensors and more capable artificial intelligence to explore the diverse worlds we find. This expansive vision transforms a one-time experiment into a sustained program of exploration, a true extension of human presence into the galaxy. To manage the flood of data from this growing fleet, we would need to construct an interstellar internet. The concept is simple yet profound. Instead of each probe screaming its faint signal across the void alone, we could deploy a network of relay stations. These specialized communication probes would be positioned at strategic points along the common routes to nearby stars, acting as signal boosters. Data from a new world would hop from the Explorer probe to the nearest relay, which would then use a more powerful transmitter to send the information on to the next relay, and so on until it reached Earth. This daisy-chained network would dramatically increase the effective data rate, allowing us to receive high-definition video and vast streams of scientific measurements that would be impossible from a lone spacecraft. The entire system, from the laser ports to the communication relays, would form a nascent infrastructure for galactic exploration, a project spanning centuries. Making this future a reality depends entirely on igniting a spark of curiosity that burns across generations. We must inspire and train the next wave of scientists, engineers, and dreamers, the children who will one day become the architects of these celestial ports and the captains of these virtual fleets. Their education will blend the fundamentals of physics and materials science with the creative problem-solving needed to overcome challenges we can only dimly perceive today. This long-term vision asks us to invest not just in technology, but in the human potential to wield it wisely, ensuring that our first step into the cosmos is followed by a journey that never truly ends. That spark of inspiration is the most valuable fuel for any interstellar journey. Just as the Apollo missions ignited a passion for science in a generation of young minds, the sight of a light sail unfurling against the blackness of space could define the ambitions of children today. This is not a secondary concern but a core pillar of the mission's success, a long-term investment in the human capital needed to sustain a project that spans decades. To cultivate this, we must bring the cosmos into the classroom and the public square. Student-built CubeSat projects offer a powerful starting point, providing hands-on experience with the fundamentals of orbital mechanics, communication, and systems engineering. These miniature satellites are the training grounds for the future engineers who will one day assemble our interstellar probes. Beyond hardware, open-source simulation software allows anyone with a computer to experiment with light sail dynamics, to feel the virtual push of photons on a digital sail, and understand the delicate balance of forces involved. Partnerships with science museums and planetariums can transform abstract concepts into visceral experiences. Imagine a full-scale, interactive model of a light sail segment where visitors can see its incredible thinness, or a planetarium show that simulates the relativistic flight through the Alpha Centauri system. The goal is to demystify the staggering scale and make the mission's grand objectives feel personal and achievable, fostering a global sense of ownership and wonder. This broad, deeply rooted support system is what will protect the project from shifting political winds and ensure its completion for the generations who will ultimately reap its rewards. With this foundation of public inspiration secured, we can look back at the other paths we might have taken to reach the stars. A light sail is not the only engine dreamed up for the journey to the stars. It is one competitor in a race of radical ideas, each with its own breathtaking potential and profound limitations. Consider the audacious concept of nuclear pulse propulsion, famously explored in Project Orion. This vehicle would literally ride a series of controlled nuclear explosions, detonating atomic bombs behind a massive pusher plate equipped with enormous shock absorbers. The advantage is raw, staggering power, capable of hurling a city-sized spacecraft across the solar system. The disadvantage, of course, is the fallout, both radioactive and political, rendering it a non-starter for launch from Earth. Then there is the fusion rocket, a more refined but equally challenging concept. It would mimic the process powering the sun, fusing atoms together in a controlled reaction to generate a continuous high-velocity exhaust. This could offer tremendous speed and efficiency, but we have yet to achieve a sustained fusion reaction that produces more energy than it consumes, let alone one compact and reliable enough for a starship. The ultimate theoretical engine is powered by antimatter. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into pure energy. This is the most energy-dense process known to physics. A few grams of antimatter could provide more thrust than the space shuttle's main engines. but we can only produce antimatter in microscopic quantities in massive particle accelerators, and storing it requires incredibly complex magnetic bottles, as it would instantly vaporize any physical container. Against these titans, the lightsail presents a minimalist elegance. Its greatest advantage is that it carries no fuel at all. This eliminates the colossal weight of propellant, which traditionally makes up the vast majority of a rocket's mass, allowing the spacecraft itself to be almost inconceivably lightweight. This is why it is the only method currently envisioned for launching a gram-scale probe. The trade-off, however, is a profound dependence on external infrastructure. The lightsail is useless without its colossal laser, a stationary beacon that can only push it on a one-way trip. It cannot slow down upon arrival, and it offers no second chances once the initial boost is over. This comparison clarifies why lightsails are the leading candidate for these first, minimally sized missions. They leverage an external power source to solve the fundamental problem of mass, turning a spacecraft into a feather pushed by the brightest candle ever lit. While fusion and antimatter represent a future of powerful, self-contained starships, the lightsail offers a path we can actually begin to engineer today, with technology already taking shape in laboratories around the world. This global effort is no longer confined to theoretical papers. Real hardware is being tested in labs and in space, driven by a small but dedicated collection of organizations. The most ambitious of these is Breakthrough Starshot, a $100 million research and engineering program. Its goal is singular and profound: to prove the feasibility of launching a gram-scale probe to Alpha Centauri within a generation. The initiative acts as a global coordinator, funding research teams across the world to tackle the core challenges, from designing the laser array to creating the light sail itself. Their work has moved the concept from the fringes of science fiction into the realm of serious scientific inquiry. Alongside this bold vision, NASA has maintained a steady, practical focus on solar sailing closer to home. Missions like the Near-Earth Asteroid Scout have tested sail deployment and navigation using sunlight, not a laser. While these sails are smaller and slower than an interstellar design, they provide invaluable data on how these gigantic, flexible structures behave in the microgravity and vacuum of space. Each successful deployment is a critical stepping stone, building the confidence needed for a much larger sail. In university laboratories, the fundamental science is being unlocked. At places like the University of California, Santa Barbara, researchers are not building full-scale sails, but are instead engineering the very atoms they are made from. They create tiny, postage stamp-sized samples of new metamaterials, testing their reflectivity, their strength, and their ability to radiate heat under simulated laser intensity. This meticulous ground-level work is where the future sail material will likely be born, in the quiet hum of a lab focused on a square centimeter of tomorrow's technology. The progress is tangible, a distributed puzzle slowly coming together. But what are the most significant technical milestones we need to achieve next to transform these scattered successes into a unified launch? The checklist for launching a starship is written in the language of breakthroughs. Each milestone represents a chasm between current ability and what is required, a gap that must be closed with years of focused effort. The first and most fundamental item is creating a sail that survives its own propulsion. Researchers must demonstrate a square meter of material that can endure a continuous gigawatt-class laser blast for several minutes without warping, tearing, or vaporizing. This is not a test of a final, perfect sail, but of a prototype that proves the core physics is manageable. Success means observing the sample hold its shape under that incredible energy flux, its surface glowing only with the heat it perfectly radiates away. Failure is a brief, brilliant flash, Parallel to this, the laser array itself must move from concept to concrete. A sub-scale prototype, perhaps 100 meters wide, needs to be constructed and tested. Its goal is not to push a sail, but to prove it can combine the beams from thousands of individual lasers into a single, coherent spot on a distant target. This validates the phased array technology and the complex optics required to focus energy across millions of kilometers. The third critical milestone unfolds in the silence of space. A scaled-down lightsail, perhaps the size of a tennis court, must be successfully deployed in low Earth orbit. This test has nothing to do with speed and everything to do with control. Can we reliably unfurl a structure of such immense area and negligible mass without it becoming entangled? The mission would monitor the sail's stability, how it responds to the gentle but constant pressure of actual sunlight, and whether its smart materials can correct for wrinkles or unwanted rotations. Finally, the probe's brain must be trusted with its own fate. Engineers must validate a closed-loop guidance system in simulations of staggering complexity. This means creating a digital twin of the entire mission, from launch to interstellar cruise, and tasking the onboard artificial intelligence with navigating it. The system must prove it can correct for course errors, recognize its target star amidst the aberrations of relativistic flight, and autonomously execute its scientific observations. Each of these milestones de-risks the grand vision, transforming an impossible dream into a series of difficult but solvable engineering problems. Achieving them, however, demands a new model of global cooperation, one where rivals become partners in a shared human ambition. The International Space Station stands as a quiet monument in orbit, a testament to what is possible when nations choose to cooperate rather than compete. An interstellar light sail mission demands that same spirit of collaboration, but on a scale never before attempted. This is not a project for a single nation or corporation. It is a human endeavor that requires a new kind of global consortium. Such an alliance would pool financial resources to shoulder the immense cost, intellectual capital to solve the staggering engineering puzzles, and technological prowess from every corner of the world. The structure of this organization would likely resemble a supercharged version of CERN or the European Space Agency, with member nations contributing funding and expertise to a central, transparent authority. The challenges, however, are as much political as they are scientific. Navigating the complex web of international relations requires careful diplomacy. The sharing of cutting-edge research and proprietary technologies, often considered matters of national security, would need to be governed by new agreements that protect intellectual property while fostering the open collaboration essential for success. Yet the benefits of succeeding are immeasurable. Beyond the scientific data, a mission of this scope could become a powerful unifying project for all of humanity. The Apollo program gave a generation a shared sense of wonder and achievement, a glimpse of our potential when we look upward together. An interstellar mission could do the same on a planetary scale, offering a positive, long-term goal that transcends borders and short-term conflicts. As we consider uniting our world for this goal, we are inevitably drawn to a deeper question, one that touches on our place in the cosmos. What are the philosophical implications of what our tiny probe might find when it finally looks back at us from another star? That first grainy image from another world will carry a weight far beyond its pixels. It will ask a question of us that we have only ever asked ourselves in stories. What does it mean to be a living world in a galaxy of silent stones? The most profound discovery our probe could make is not a city or a signal, but a simple chemical signature in an alien atmosphere, the unmistakable fingerprint of biology. Finding that we are not alone would be the single greatest revolution in human thought since we understood that the Earth revolves around the Sun. It would transform biology from a local science into a universal one, suggesting that life is not a fragile accident, but a fundamental force in the cosmos, a natural outcome of cosmic chemistry. Philosophers note that such a discovery would force a radical expansion of our empathy, stretching the concept of community to include beings we may never meet, from a world we may never walk upon. The very word life would forever change its meaning, but the opposite finding could be equally transformative. What if, after surveying our nearest stellar neighbors, we find only barren rock and sterile gas? A cosmic quiet would settle over our collective consciousness, a sobering realization that life might be an exceedingly rare and precious phenomenon. This knowledge would not diminish our world, but could instead bestow upon it a new and profound sacredness. Our planet would become a sanctuary, a tiny, vibrant garden in a vast and silent desert, making our responsibility for its care feel more urgent than ever before. History shows us how deeply such astronomical shifts can resonate. When Copernicus moved the Earth from the center of the universe, it did not just change our maps of the sky, it fundamentally altered humanity's perception of its own importance, triggering revolutions in art, theology, and philosophy. A discovery of life or its absence would be our modern Copernican moment, challenging our deepest narratives about our own significance. Preparing for this psychological and cultural impact is as crucial as designing the probe's antenna. Mission scientists are already consulting with historians and ethicists to frame how such discoveries would be shared with the public, ensuring the news fosters global understanding rather than fear. This long-term perspective weaves together every thread of the mission, from the physics of the sail to the programming of its artificial mind, into a single, coherent vision. It is a vision of a species mature enough to build a machine that can cross the void, and wise enough to understand the message it brings back, whatever that message may be. Every gear in this cosmic clock must turn in flawless synchrony. The sail cannot be designed in isolation from the laser, nor the probe's brain developed without considering the immense delay in its communication. This is the domain of systems engineering, a discipline dedicated to viewing the mission as a single, integrated organism. It forces us to ask questions that cross traditional boundaries. How does the heat absorbed by the sail during acceleration affect the performance of the miniature instruments nestled at its center? If the onboard artificial intelligence decides to reprioritize its data collection, how does that altered transmission schedule impact the power draw from the nuclear battery? Every decision ripples across the entire design. To manage this complexity, engineers rely on incredibly detailed digital twins, virtual replicas of the entire mission that exist only as lines of code. These simulations run through thousands of scenarios, from a successful flyby to a catastrophic micrometeoroid strike. They test how the flexible sail deforms under the laser's push and how the guidance system corrects for that deformation. This virtual proving ground is where we discover that a material perfect for the sail might create problematic static electricity that interferes with the probe's sensitive magnetometer, forcing a redesign before any metal is ever cut. The process is relentlessly iterative, a cycle of design, model, test, and refine that repeats for years. Subsystems are constantly validated not just for their individual performance, but for how they interact with every other part of the machine. A weakness in the international legal framework governing the laser's use is just as critical as a weakness in the sail's molecular structure. Both have the power to halt the mission entirely. This holistic perspective is what transforms a collection of brilliant technologies into a viable vessel, a single entity poised to step into the light. With this complete design finally in view, we can turn our eyes to the moment of launch itself and the legacy it begins. We have walked the long road from microscopic materials to cosmic law, a journey proving this is far more than an engineering puzzle. It is a tapestry woven from the threads of physics, ethics, international cooperation, and the enduring human drive to explore. This mission stands as a collective statement, a declaration that our species chooses to look outward, to seek connection and understanding across the vast ocean of space. The visionary Carl Sagan captured this spirit perfectly when he reflected that somewhere, something incredible is waiting to be known. Our task is to build the vessel that will go and find it. This grand adventure now extends its invitation to you. Let this exploration spark your own curiosity and become a voice of support for turning this dream into reality. We want to hear your vision for our first destination. Share in the comments which star you believe we should visit first, and subscribe to join our community as we continue mapping the path to the final frontier.